Welcome back to ECE 320A. Homework number 6 is due a week from today, and that will be really you have the material to work that, I think, already. We'll go over a little bit more of that in terms of incorporating initial conditions into S-domain circuits. We'll talk about an overview of transfer functions, a generalized idea of what that is, and we will start to begin dealing with convolution by deriving the convolution integral. We'll see if we get that far, but you might start watching. There will be supplementary material on convolution on D2L. And how many of you have seen convolution before? A few brave souls. The others are not willing to admit to seeing it. Well, we'll get through it, and we will work through that process, if not now, in future lectures and on the D2L website. I'll give you additional information or videos and notes on D2L beyond what is done in class. Let's now start by looking at the idea of incorporating initial conditions into S-domain circuits. We talked about this in last class. Whoops. But last time we actually focused or emphasized the serial source or serial sources, voltage sources for the inductor and the capacitor. Let's look at how we can generalize that and actually have the opportunity to incorporate initial conditions either in series with the impedance element or in parallel with the impedance element. And that will give us more flexibility when we're thinking about analyzing our circuits. With respect to the inductor, here is our schematic that we are hopefully very comfortable with. And that relates then the direction of the current relative to how we've defined the polarity on our inductor. And that's all consistent with Eli, which says that the voltage dropped across that inductor is proportional to the time rate of change of the current going through that inductor. That's now our time domain version of the inductor, and we want to be able to put that into an S-domain equivalent. The S-domain equivalent is found by simply Laplace transforming that current voltage relationship. If we do that, then we scale the Laplace transform of the derivative of the current of the inductor, which is S I sub L of S minus I sub L of 0 minus. If we now distribute that L across both terms on the right-hand side, we now have this voltage relationship of our inductor in the frequency domain made up of two pieces. A piece involving the impedance of that inductor, which is S times L. S is our complex frequency variable, and a piece due to the initial condition. And both of those are making up the total Laplace transform voltage of that inductor. If we now, and this is what we looked at last time, which is the S-domain series circuit of the inductor, and that we can simply write down by inspection, or if we forget how that's all related or interconnected, we can simply rewrite KVL. But here is my impedance of the inductor, SL. I'm going to assume now that my current in the frequency domain is flowing consistently with the direction that I defined in the time domain, and my voltage dropped across that inductor now has to contain both pieces that make up that description, and I get the first part on the right-hand side by multiplying that impedance SL times I sub L of S, and then I go into that voltage source, into the minus terminal, and the voltage source has a value of L times I sub L of 0 minus. That's now, if you were writing mesh equations, you would probably want to incorporate your initial conditions on these inductors as voltage sources in series with your impedance element. If you wanted to write node voltage equations, then you usually don't like to have voltage sources. You would prefer current sources. And we can derive that also. We can now look at the S domain parallel circuit for the inductor. Meaning, if we have this governing relationship, V is equal to SLI minus Li sub L of 0, to get the parallel circuit, let's solve this equation for the current, I sub L of S. Doing that, which is really just dividing all the terms by the impedance, SL, of that inductor, we now have 1 over SL V sub L of S, so our impedance is in the denominator, which is sort of what we're used to seeing, plus, and now if we divided both sides, or that last term on the right, by SL, the L's cancel, and I'm putting that term on the other side of the equality sign because I'm solving for I sub L of S. I now have a plus I sub L of 0 minus over S. And this is now my governing relationship for the circuit schematic in the frequency domain if I'm trying to incorporate a parallel current source with this impedance of the inductor. I can use this formula. Meaning, and the way that I find it easiest to think about is, here's my inductor current, and I actually have two parts to that current. One part is associated with the impedance of the inductor itself, SL, and the other part is due to the initial condition. And all of that, if I wanted to know or keep track of the voltage on that inductor, it's now across those two parallel elements, a source and an impedance. And what's the labeling of that source is going to simply be I sub L of 0 minus over S. And which direction do I want the current source to be moving? From left to right or right to left based on this governing equation. And now I could simply think of writing KCL at that and saying what's entering the node and what's leaving the node. Entering is I sub L, the blue on the left. Leaving is the current V sub L over SL up top through the impedance, and also leaving is that current due to the initial condition on my inductor, which has as its value I sub L of 0 minus over S. That's not the same value that the voltage source had in the series circuit. So depending on which of these you use, which of these schematics you use to replace your inductor in your S-domain equivalent, it influences how you now label that source. And what type of source also is dependent on whether you're looking at the series or the parallel combination of the sources. Is that clear? You write node voltage equations, you probably want to use this schematic and drop that into your circuit where you had an inductor. If you were writing mesh equations, then you say, oh, I'm going to put this combination, this series combination with a voltage source incorporating my initial condition, replace my inductor with that. And we can do the same kind of analysis for the capacitor. And let's just quickly go through that. With our capacitor, we have let's say the conventional representation in the time domain. Let's say here is our capacitor current, I sub c of t. There's the capacitor, and then my voltage drop, or the voltage drop on that capacitor, labeled consistently with the direction of that current, is V sub c of t from plus to minus. And with ice, we know that that's I is equal to C dV sub c of t dt. And that equation is then consistent with how that capacitor is labeled, both current and voltage. That's the governing current-voltage relationship of a capacitor. If we Laplace transform that equation, now we have C times S V sub c of S minus V sub c of 0 minus, or we now have SC times V sub c of S minus C V sub c of 0 minus. Or if you're not used to seeing it that way, you could say, well, I have typically when I think of my impedance, maybe I say, well, what's dividing V sub c? It's my impedance. Well, to get SC, I need to divide by 1 over SC, and that's now my impedance of the capacitor, minus C V sub c of 0 minus. In this case, the way that this fell out of my current voltage relationship, this is immediately screaming at me, this is the parallel connection structure, because it's all defined in terms of my current, I sub c of S. Meaning I now have the parallel S-domain circuit for a capacitor from this relationship. Here is the I sub c of S. It's again made up of two pieces. One piece results from the impedance of that capacitor. Another one is going to be contributed by means of a current source. Here is my current of the capacitor. Here's my impedance of the capacitor. I also have this voltage drop in the S domain, V sub c of S. And now what do I do with respect to my current direction in that current source? I need the algebraic sums to give me that equation. And if I said, oh, the left-hand side is entering the node, the right-hand side is leaving the node, then the 1 over SC is okay, because that's in the plus-minus polarity direction. But now, in terms of leaving, I have a minus leaving. Well, that's sort of the negative, which says that this particular current source for the capacitor now needs to be directed back into the node, and it now has a value of C V sub c of 0 minus. Are we okay with that? And this is this schematic that you would use in the S domain if you were writing what kind of equations? KCL, or node voltage equations. If you were applying KCL throughout your circuit, you would probably want to be plopping this schematic into your circuit where the capacitor was. And this is what we looked at last time, which was the series connection. Maybe we didn't derive it, but we used it. In this case, we now need to solve for the capacitor voltage in this earlier expression, and I can do that by multiplying everything by 1 over SC, and I now have 1 over SC times I sub C of S plus, and if I multiply minus C by 1 over SC, what do I get? So my C's cancel, don't they? And I now have this, and I can't lose track of the sign, V sub C of 0 minus over S. Whoops. Can't lose track of the sign. What happened? Well, I was solving for V sub C, and that's on the right-hand side, and I want all the other terms on the left, so that I added CV sub C of 0 onto both sides, and that's why I now have a plus sign on that particular term in my expression for the capacitor voltage, V sub C of S. And now this one's fairly straightforward to sketch. Now I have my capacitor and its impedance. I have the current of the capacitor, and then I have a voltage source consistent with this expression. And what do I need for that polarity labeling inside that voltage source to look like? Is the positive sign on the left or the right, according to this equation? And if we forget, if you put that in on the left, then what you can do is you could just check your work and say, oh, let me just make sure that I put that in the right place, and you can just write a KVL equation. You can say minus V sub C plus 1 over SC I sub C plus V sub C of 0 minus over S, and yes, that's the correct polarity. Questions on these models? We now have 4 models, and is it clear how you select between those models? Do you have a 4-headed coin and you flip it and you say whatever it is, that's what I'm going to use? So now I have an inductor and I use a capacitor model. No, you probably know to use the capacitor models. But which circuit model you use depends on what kind of analysis you're performing or wanting to perform. Which circuit model is used depends really on what you like to do, on personal preference, and whichever, let's say, and the particular situation you find your circuit presenting to you. If you have a bunch of meshes, then you say, oh, I really do want to write some KVL equations. Then you're going to be opting for the 2 series combinations where you have voltage sources that incorporate your initial condition. Likewise, if you were applying KCL equations or doing nodal analysis, that's when these parallel connections are more appropriate, or when we might apply then parallel current sources. And that doesn't take a 4-headed coin. Okay, that's exactly where I wanted to be at this point. Are there any questions on this material? Actually, we have no time for questions. No. Are there questions? Are we okay with this? This is all you're getting for S-domain circuit analysis. Now you're experts. You can do it with matrices, you can do it with coupled sets of equations, but now those equations involve S, this complex frequency variable S, and you just do your analysis, you end up with an equation. Now it's now a V sub C of S, and you need to find what that capacitor voltage is in the time domain. Oh, just look in my table, inverse Laplace transform, and you have your capacitor voltage as a function of time. And you now know how to incorporate all the different initial conditions. And you can obtain those initial conditions by looking at limiting behavior in your circuit before a switch gets thrown, for example. Now we're ready to move on and generalize some of these ideas by introducing the topic of a transfer function. We've been using transforms, ratios of polynomials in S. The transfer function is just a generalization on that concept. Here's our definition. And it's really just an equation definition. H of S, which we will call our transfer function, is just a ratio of Laplace waveforms or signals. We take the Laplace transform of our output time response and divide into that the Laplace transform of our input time response. The reason it's called a transfer function is because this allows you or tells you how information or signals get transferred between the input and the output. If you now multiply this transfer function by an input signal, that will produce the output signal corresponding to that particular input. But if you find the transfer function of a circuit, you don't have to reanalyze the circuit every time somebody gives you a new input. All you have to do is transform or work with the new input and this transfer function to produce the resulting output. So now you have this in your pocket or on your engineering pad, this transfer function, and now somebody can give you whatever input they want, and you can now figure out what the output is for that input. The nice thing about this transfer function is it's not just for circuit analysis. Now you have the whole universe of dynamics to play with. So what H of S represents depends, obviously enough from the definition, on the input and the output. And if you wanted a visual to sort of keep track of, you could think of this block diagram. Here is your input, here is your output, and they are related by a product of H of S with X of S. Here is your system, here's your input, and there's your output. In circuit analysis, our input might be a voltage source. And now we've analyzed the circuit and we found our transfer function between that input voltage source and maybe the current flowing through this third inductor in our circuit. And that's our output. Now we have that transfer function. We can now think of it in terms of this more general block diagram. Now we have an H of S that models our circuit. Now in that circuit, You could have all sorts of different outputs. Maybe you were interested at one point in the output of that third inductor's current. Maybe somebody else is interested in the voltage across that second capacitor in your circuit. Well, there's two different transfer functions in the same circuit. That's okay. You can have many different transfer functions in just one circuit. One circuit for this class, or in general, one system, can have several transfer functions associated with it. Now, to broaden our perspective on this, let's just list some possible inputs and outputs, and we could actually match these up in whatever combination we might be interested in or might present themselves in our particular circuit or system. Let's say the left-hand column, we call these inputs. In the time domain, those would be x of t's. And on the right-hand side are maybe some variables that we will consider as outputs and y of t. In this class, maybe you would think of current as an input, or maybe you have a voltage as an input. Maybe you have a mechanical system and the input is actually a force. Or maybe in that mechanical system your input is actually a velocity. Or maybe it's an angle. It's on some dial and you're changing the input and it's now an angle. Or maybe it's the position and you now know what the position or that mass location is as a function of time. Those are all potential inputs. What are outputs? Well, we could be interested with currents through different circuit elements, or voltage drops across those, or maybe in a mechanical system we're interested in the force, or in an electromechanical system that machine is now delivering a certain force somewhere in our entire system. Maybe we are interested in keeping track of an acceleration, and that might be an output. Or maybe a velocity, or an angle, or a position. And we could have all sorts of transfer functions, and here you could just connect the lines. Meaning you could have a current for an input and a force as an output. Or you could have a current as an input and a position as an output. Or you could have a velocity as an input and a current as an output. You see all the different possible H of S's that you could be working with or living with. Let's look at one from a system that you should be very comfortable analyzing. A hydromechanical electrical system. No. Everybody's had their dynamics, right? Maybe it's an electro-hydrodynamic system. We'll throw some optics in. No, let's just look at this RLC circuit, because I want you to feel the weather's getting a little bit cold outside. I want you to remain warm and fuzzy with these concepts for the transfer function. Here's your RLC circuit. And if you were in an interview and somebody said, "What can you tell me about this circuit?" what's one of the first things you might comment on? has two energy storage devices, which translates into second order differential equation. And now you'll say, would you like me to solve a second order differential equation? And is that circuit underdamped? Is it overdamped? Is it critically damped? You have all those options for this, just this basic circuit. And we will look at maybe having two different outputs. Maybe the current through each of those elements that results from this voltage source, V sub G of t, or maybe somebody says, no, I just want to know what's the voltage of that capacitor when I put in this voltage source, V sub G of t. Now, if we're interested in transfer functions, you're going to like this. When we push it down into the S domain, equivalent circuit, if we're just interested in the transfer function, we can neglect the initial conditions. So now we don't have to do what I just lectured on 20 minutes ago. We simply replace the R's, the L's, and the C's with their impedances. We forget the initial condition pieces. And that's okay, because we're just trying to find the transfer function. We're not wanting to know the transient information or the information due to the initial conditions. If I do that, what does the circuit look like now in the S domain? I'll do the hard part. It looks exactly the same as what you started with, doesn't it? Except now we incorporate generalized impedances for these different circuit elements. The resistor goes through unchanged. What's the impedance of the inductor? That's just SL. And remember, S is a complex number. It's a function of frequency. So instead of, when you were in chapter 9, you were just looking at sinusoidal steady state, and you had an impedance of j omega L. S now can have a real piece. It can be a sigma plus j omega. And that's now multiplying L, and we just collapse that or collect that into one complex variable S, SL. The impedance of our capacitor, 1 over SC. And now we can keep track of this series current or the capacitor voltage. But now that we have this modeled in the S domain, now really this is just almost going back to day 1 in 220 with respect to how we analyze circuits. All of these circuit elements are associated with generalized impedances, which are just glorified resistors, except now these resistors are variables or functions of frequency. That's where the S's come in, and we just keep track of the S and it all takes care of itself. If we had 3 resistors right there, how would you solve for the current? You would add all those resistors up and divide them into the voltage source, wouldn't you? Well, that's exactly what we're doing, except we're doing it with these impedances. So I of S, this series current, is just V sub G of S over R plus SL plus 1 over SC. And if we want the transfer function between the voltage source, V sub G, and the current I, now we could divide both sides through by V sub G, or we could perform that ratio that we had the definition from. Let's do it the definition way, which you don't need to do, but we'll just do it the long way for now. H sub 1 of S, our first transfer function for this same circuit, is now the output, which we said in this case was our current, series current, and our input is V sub G of S. But we've just defined I. I is V sub G of S over R plus SL plus 1 over SC, and we divide that by V sub G of S. Well, that's nice because you shouldn't be having any signals in your transfer function. Those signals cancel, and now H sub 1 of S becomes 1 over R plus SL plus 1 over SC, but that looks a little bit odd. We don't usually have rational expressions in the denominator, so we clean all of that up by multiplying both top and bottom by 1, which in this case 1 is SC. If we multiply the numerator by SC, we multiply the denominator by SC and rearrange the terms, we have an S squared LC plus an SR plus, multiplying by SC, so I have an S times RC plus 1. Questions on that? And that's now our first transfer function. Is that transfer function stable? How do we know if a transfer function is stable? Where do we want the roots of which polynomial where? Do I have enough questions? You need them in the left-hand side of the complex S-plane. Can we tell anything from this? This is just a bunch of variables. Can we say anything? What's your inductor value, L? It's a positive number, isn't it? What's your capacitor? Positive. What's your resistor? Positive. So now if we factor out LC and obtain a monic polynomial, which just means your leading coefficient is normalized to 1, and put the LC upstairs maybe, now we have an S squared plus an S times R over L plus 1 over LC. Those two coefficients are present and positive. So you know this is a stable transfer function. And you could have known that by just, somebody gave me an RLC circuit. I have positive resistors. That's just going to dissipate energy that I put in. It's a positive, or it's a stable transfer function. But the denominator is now the roots of that quadratic. And that quadratic, depending on your R, C, and L, could be 2 real roots, or it could be 2 complex roots. Okay? If you didn't have a resistor, you would lose that middle term, and what would you have? Pardon? You'd be right on the vertical axis, right on the imaginary axis, wouldn't you? And what happens when you have something right on the imaginary axis in terms of its stability? No decay. It just sits there and shakes, doesn't it? So you would have built an oscillator. If you have a capacitor and an inductor without any resistance, which in a real system you have some kind of dissipation, but if you don't have any resistance, now you have a pure oscillator. Now you know how to build an oscillator, and you know how to pick the frequency of that oscillator by the choice of L and C, your inductor and capacitor value, just by that second order circuit. So you could go into your interviewer and you could just keep going and going and going, right? You could even start sketching Bode plots after a few more lectures from this. Just a simple second order equation. All right, so that's one transfer function in that circuit. That's just I, the output being the current through that series loop. We could say, well, no, I want a different transfer function for the same circuit, but I want my transfer function to be between the source, V sub G, and that capacitor voltage, V sub, what am I saying? The source, V sub G, I need to enunciate. Did I say the wrong thing before? thought I said V sub c. Maybe not. I'm sleeping. I couldn't even remember if I took out the garbage this morning. Stressed about that. Eating breakfast and going, did I remember to take out the neighbor's garbage? I take her garbage. She's a little older, so I help her out. I got to worrying about that while I'm eating my breakfast. Where am I? Sleeping. That's where I'm at. So now, what? Oh, V sub g and V sub c. The transfer function between those. She watches these YouTube videos, so she'll get a kick out of that. I doubt it. But I think, yeah, never mind. What do we want? I know, you want to go home. No, don't be thinking that way. This is fun stuff, right? So we want to find h sub 2 of s. A second transfer function for the same circuit. And this one we are defining to be, now, some students get confused. Where's the output in this transfer function? It's up top, isn't it? The bottom is the input, because if you now multiply this by the input, you want it to produce the output. That's one way of thinking of that or remembering that ratio. But what's V sub c of s? If I just said, oh, give me V sub c of s, that's just the capacitor's impedance, 1 over SC, times the current. We found the current. So I could write it that way. I could say, well, that's just the capacitor's impedance, 1 over SC, times I of S. But what was I of S? That was this, wasn't it? So now if I write that down, I have V sub g of S over that sum of impedances. And that SC getting multiplied in the denominator cleans things up pretty easily. Now I simply have for the capacitor voltage, V sub c of s, that's V sub g of s, all over s squared LC plus s RC plus 1. And now if I wanted the second transfer function, which is the ratio of the output that I'm interested in this case V sub c of s over V sub g of s, I could start with that equation that's visible at the top of the page and divide both sides by V sub g, and I have my transfer function. The transfer function now is simply 1 over s squared LC plus s RC plus 1. Do you notice anything about h sub 2 relative to h sub 1? Now you're playing this game of match, huh? Are there anythings in h sub 2 that match or look like things in h sub 1? The denominator is exactly the same, isn't it? Well, it's the same circuit. It has the same natural behavior. It's just where you're looking in that circuit, it's going to give you something different. In one case, we were measuring the current. In another case, we were measuring the voltage. So we may see something different, but naturally that circuit's going to just shake the way you've selected R, L, and C. And that's going to be given to us by the denominator. And we actually give that a specific name. What did I say? I said that denominator sort of provides us the natural or the characteristic behavior of our circuit, and so we call that actually the denominator polynomial, the characteristic polynomial. That's equal to the denominator polynomial. And that's the same in both transfer functions. Because it's coming from the same circuit, you better have exactly the same characteristic polynomial in all your transfer functions associated with that circuit. So the characteristic polynomial, which is equal to the denominator polynomial, is the same in h sub 1 of s and h sub 2 of s. Let's now write down some properties of transfer functions. Knowing what we already know from earlier discussions. One is that linear lumped parameter circuits yield rational transfer functions. And you wondered why I was talking about breakfast. So now we have oatmeal in our circuit. We have lumpy oatmeal. What? What's it mean for a lumped parameter? I didn't think we were dealing with oatmeal in this class. Or breakfast. Usually we have pies floating around, don't we? Hungry. What's a lumped parameter? Do we know? What oatmeal-ish about that circuit that we just talked about? Well, lumped parameters, let me maybe give you a little bit of a that means that you have discrete components. That means you have a discrete resistor. You go to Josie and you get a resistor. You don't have to worry about the resistance throughout that entire line in the frequency range that we're analyzing the circuit with respect to. We don't have to worry about the inductance of that entire line because of the frequency that we're dealing with. The frequencies that we're dealing with have wavelengths that are huge relative to these circuits that we're building. And because of that, we can lump all of this resistance into one element. We can lump all of the inductance into one parameter. We can lump all of the capacitance into one capacitor. They're lumped parameters. We don't have to worry about those being distributed across or around in the entire circuit. Unlike if you take 381, where you're dealing with a transmission line, that transmission line is huge in length, and it might be somewhat in the same ballpark as the wavelength of that frequency going through that transmission line. What's the frequency going through the transmission line? 60 hertz. What's the wavelength of that 60 hertz? What's the relationship between frequency and wavelength? Speed of what? Speed of light, right? C is equal to d lambda, or F, I'm sorry, F lambda, I can't see them. So the frequency times the wavelength is equal to the velocity. So you can divide that out, and you'll find that the wavelength is quite long for 60 hertz, right? What's the speed of light? 3 times 10 to the 8, roughly, right? Meters per second. Divide that by 60. That's not dividing by much, is it? What's your wavelength? What's lambda? On the order of 10 to the 6th, 1,000 kilometers, right? That's 1,000,000 meters. 1,000,000 meter dash, sorry. Didn't quite get it out. That'd be far, wouldn't it? Don't want to sprint that far. Maybe 100 meters, not 1,000,000. Okay? So 1,000,000 meters. Relative to our circuits, I think we can neglect, or the wavelength's pretty long. Okay? That's what we're meaning by lumped parameter. Ooh. So discrete components are not the same as distributed components. Now, if you're dealing with optical waveguides, then maybe you can't lump your parameters. Maybe you have to worry about partial differential equations. All right, let's move on. Number 2. But we now know what? If we have oatmeal, we can play with ratios of polynomials in S. That's what we said, right? So we have a polynomial in the numerator and we have a polynomial in the denominator if we have lumped parameter circuits. 2. This is probably going to be your favorite. Well, maybe you like the lumped. Transfer functions are obtained or computed or found or derived under 0 initial conditions. So you can throw away the first half of this lecture when we're talking about transfer functions in terms of finding the transfer function. 3. Spent too much time on that oatmeal, so we have to keep going pretty quick. Is that clear? So anytime you ask for a transfer function, don't worry about the initial conditions. That simplifies your circuit, it simplifies your analysis. 3. The poles of h of s, are those the roots of which polynomial? Numerator or denominator? That's downstairs, isn't it? It's the denominator. The poles are downstairs. So the poles of h of s govern the natural response or you could think of the transient response if you simply hit that circuit with a transient input and watched it decay. That's its natural behavior. Poles of h of s govern the natural response or the transient response of the system. Meaning, if your interviewer gave you a circuit and he gave you RLC values, and you found the roots of that quadratic, now you can tell him something about the transient behavior of that circuit, how it naturally will behave. For example, if I gave you the following, maybe I said the poles of a circuit that I'm going to give you are at s equal minus 1 and s equal minus 6. What's the structure of your natural response? So now you have, can you envision what you have as far as a transfer function? If you have a pole at -1 and a pole at -6, first, what's the order of that system? Second order, it has two poles. The number of poles is the order of your system. You have two poles, you have a second order system. Now, if you have two poles, that means I have one factor that vanishes when s is equal to -1. Oh, that's an s plus 1 factor. I have a second factor in my denominator that vanishes when s is equal to -6. Oh, s plus 6. In my denominator, I now have s plus 1 and s plus 6. Exactly. Now you know how this looks in the time domain because you can inverse transform that. You now know that y of t is going to have one term that looks like 1 over s plus 1 inverse Laplace transform, and the other term coming from the pole at -6. So your system naturally shakes at e to the minus t and e to the minus 6t. Those are its two modes. And you then, depending on how it's interconnected, that will influence A and B, the relative weights of those two modes. We've already talked about point 4. The denominator polynomial equals, what else do we call it? We also might refer to that as the characteristic polynomial. Five. How many of these do I have? Can I reset the clock? Give us another hour? I have 20 more pages to work through. 15 more points. Uh-oh, somebody's leaving. I'm teasing. 5. A stable system. This is the next to the last, okay? We have 6. I was just kind of getting you ready, conditioned to. We're done. All right. Point 5. A stable system has what? It has all of its poles where? In the left half plane, left half S plane. And I may just, because you guys might be wanting to communicate this efficiently, you might just, in your text messages, say LHP. Right? When you're communicating with friends, you might say, this party is LHP. That may be a good thing or a bad thing, but now you have a stable party. Right? That means you have some damping. Right? That means things start to decay after a while. Right? Never thought of a party that way before, huh? You never know. What else do we know, though, about point 5? So now I have 20 parts to point 5. Tricked you, didn't I? A passive, that means we have an RLC circuit, a passive RLC network. That means we do not have any energized elements like op amps, anything that require a separate source. Passive RLC networks produce stable transfer functions. So if you derive a transfer function from an RLC circuit, a passive RLC circuit, and you end up with poles in the right half plane, You go, oh, I must have an algebra mistake, or I must have an error somewhere, because if this is a passive RLC circuit, I better be having all of my poles in the complex left half S plane. Six, the zeros of our transfer function h of s are the roots of which polynomial? They're upstairs, aren't they? They're in the numerator. So the zeros of h of s are the roots of the numerator polynomial. Of h of s. Here's something else you might want to text. If the finite zeros, and that means they're not at infinity, so they're bounded, if the finite zeros of a stable transfer function h of s, if the zeros, in addition to the poles, are in the left half plane, or in the LHP, we're texting again. So now if the zeros are in the LHP, we have a special name for that system. The system those systems are called minimum phase. Here's our complex S plane. Suppose I have a pole here and a pole there. Is my system stable? If I have a zero there, is my system stable? And we have another way of describing this system, don't we? This system is minimum phase because the zero is also in the left half plane. What do you mean minimum phase? We are going to be, we've talked about the circus in here, haven't we? The big top tent, the rubber sheet, thumbtacks and poles. All right. To find the frequency response, and when I say frequency response, what are you thinking? How much more time do we have? No, when I say frequency response, what are you thinking? How does this circuit behave relative to different frequencies? Or how does this system behave for different frequencies? Your stereo has possibly a graphic equalizer on it, has some knobs that you can change the frequency behavior of the source, and now it comes out. Maybe you really want to hear the vocals, and maybe the bass you don't want to hear, so you reduce the bass. You maybe heighten the high frequencies, the treble, and maybe the mid-range you leave flat. So now you have a frequency response that your source has to pass through before you hear it, right? So now your circuit or your system has a frequency response. We can find that frequency response magnitude by examining the contribution of the poles and the zeros as we walk up the imaginary axis. The frequency response is going to be found from our transfer function h of s when we replace s with j omega and evaluate for different frequencies omega. Meaning, in this particular circuit, or block, this S-domain picture, maybe this is -2, and maybe this is J1, and maybe this is -1. What's our transfer function? We don't know the magnitude, do we? Or the scaling factor, but we do know that we have a 0 at 1, and we have two poles that are conjugates, complex conjugates. They have a real part of 2 and an imaginary part of 1. So they naturally like to shake at 1 radian per second. That's their damped frequency. Their decay is influenced by e to the minus 2, and the 0 is at minus 1. Now, what I'm saying is when we want to look at the frequency response, we now are looking at h of j omega. We replace s everywhere with j omega, which is really equivalent to saying I'm going to look at what happens when I simply walk up this frequency axis, and whatever happens at certain frequencies, that's how that system is going to either amplify or attenuate the behavior at that frequency. And so I could then think about that 0 contributing that much information in magnitude, the distance from that 0 to that frequency, j omega x, let's say, and I have all the contributions due to those poles, and I'll divide that 0 length by the pole lengths and scale that by a, and that's my magnitude at that frequency. I can also associate an angle with each of those singularities, or pole and 0 factors. I'm trying to explain minimum phase. Please be tolerant, okay? So I'm getting there eventually, but I thought this was so fun, talking about the circus and the big top tent. So if you walk along the imaginary axis and you look up at that surface above you, which is the rubber sheet that's stretched on top of those 2 infinitely tall poles, and that 0's the thumbtack at minus 1, that's what the magnitude looks like. The angle is going to be the angle contributed by each of those, and the angle of my 0's will be in the numerator. My angles of the poles will be in the denominator. And angles in a ratio simply add and subtract, don't they? Angles in the denominator will be subtracted from angles in the numerator. Now, if I had not a 0 at minus 1, but a 0 at plus 1. So now virtually erase that 0 and pretend that we have a 0 there. That system, what's the distance between that 0 and j omega x and the stable 0, if you can kind of say, or the 0 in the left half plane, minus 1 and j omega x? What's the difference between those lengths, hypotenuse? Tharp, I think that's the same. It's like Pythagorean theorem. Have the same distance horizontal, same vertical, a squared plus b squared, hypotenuse, same length, right? So the magnitude response looks the same if you have 0's exactly opposite the vertical axis in the right half plane versus the left half plane. But what do we know about the phase? The phase we measure with respect to a horizontal line in the real direction. So the phase of that angle, or that 0 at minus 1, is, in this case, a little under 45 degrees if I'd scaled it right. Because if I went all the way up to J1, that would give me 1 and 1, a 45-degree angle. That angle theta is less than 45. But the angle of this 0 in the right half plane, even though it produced, that 0 produces exactly the same magnitude behavior, what happens to its phase? measured from the positive real line emanating from that singularity, that phase is not minimum, is it, for the same magnitude? That's why we call them minimum phase systems if our zeros are in the left half plane. Now, how many of you rode a bicycle today? Those are non-minimum phase systems. And they're more difficult to stabilize than minimum phase systems. And you'll learn about that in controls classes. And 442 is a controls class in the spring that you could take just based on having 320. We've changed 340, so now we have to change 442 so that you can take it after taking this class and nothing more. Just commercial information. Where were we? Is it clear what we mean by minimum phase systems now, or where that concept comes from? Maybe it's not real clear, but I want you to start thinking about these ideas because you now know how to draw Bode plots based on what we've talked about just now. Maybe you don't know it, but I've given you a fair amount of information. I've told you how to compute magnitudes for each of these different poles and zero factors. I've told you how to compute angles just graphically from this S-domain picture. And that's really what we will learn how to do, maybe more systematically, by Bode plots. We'll learn how to sketch those very quickly once somebody gives us the poles and zeros of a transfer function. But now, if you needed to, by brute force, you could do that. If somebody gave you the A in my transfer function, you could tell me what the magnitude of that transfer function was at a frequency of 2 radians per second. What would you do? You would run up the imaginary axis to where? To J2, right? You wanted the frequency response at a frequency of 2 radians per second. You would go to J2, and then you would find the length from that 0. That would be in the numerator. That's the magnitude due to that 0. Then you would take that pole in the second quadrant and find its distance to J2. That's one of the pieces in the denominator. Then you would take the distance from this pole in the third quadrant to J2. That's a little longer, isn't it? That now has a length that you would divide into the zeros length, scale it all by A, and now you know the magnitude in real terms of your system at a frequency of 2 radians per second. If you wanted it in dB, you would simply take 20 log of that value. And that's what we will sketch in the Bode plots. If I now said, what's the magnitude response at 10 radians per second? You know how to compute it, right? I would have to run through the wall if that was 2 before. And that wouldn't be pretty. Wouldn't feel very good either. And I don't think I'd get very far through that wall. Wouldn't even touch that. Well, I'd touch the wall maybe. Might end up with a red nose. Bloody nose. So I don't have a helmet. Where were we? Bode plotting. Is it sort of clear what you can do with this S-domain picture of poles and zeros? It's very powerful. It gives you a good visual and a good understanding. We'll pick up with convolution on Tuesday. Wow, this is Thursday. Have a safe evening tonight.